All right, so what we're going to do today is that I'm going to start talking about the development of atomic theory. So in the next few minutes, I'm going to whiz through the observations that led to the belief that atoms were the most basic constituent of matter. And then what we're going to see is that the atom can actually be split up, that the atom is not the most basic constituent of matter, that there's at least an electron and a nucleus. And we're going to start talking about what are the fundamental principles that have to obtain in order for that electron and nucleus to hang together, to remain an entity. And what we're going to see is that we're going to have to understand a new kind of mechanics to understand how that electron and nucleus hang together. And then further on in the course, we're going to need that new kind of mechanics to also understand how two atoms hang together, how two atoms bind to form a molecule. All right, but today I'll lecture for the first 2/3 or three-quarters of the course, and then I'll stop, and then I'll introduce the rest of our teaching team, and we'll talk about the mechanics of the course, we'll talk about the expectations of the course, and some details like that. Okay? Okay, so let's get going here. And now we could turn the lights down, because I am going to use the slide here in the front. All right. So the ancient Greek philosophers, they certainly were known to have pondered whether matter can be divided endlessly into smaller and smaller pieces, or whether there was a point at which you couldn't divide matter any further. And Aristotle here, well, he was one of the philosophers who argued that matter could be divided into smaller and smaller particles, chopped up into smaller and smaller pieces, ad infinitum. Matter was divisible. This is called the continuum theory of matter. Continuum because you don't have any discrete points. It's a continuum, no boundaries. All right? But there was a contrary philosophy heralded by Democritus, who actually was about 100 years older than Aristotle. And he held that matter, indeed, was composed of individual discrete particles. These discrete particles he called atomos. For not, tomos for divisible. That's the origin of our word, of course, atoms. Now, in the 4th, 5th century BC, there wasn't much evidence one way or the other for these kinds of, either one of these philosophies. And I call it a philosophy because it was a search for understanding reality by a speculative as opposed to a investigational or observational means. But for whatever reason, it was Aristotle here, his continuum theory of matter prevailed all the way to the 17th century. And here, in fact, he is depicted by Raphael on a fresco on the walls of the Vatican, holding court, the continuum theory of matter. But just about at the same time at which Raphael painted this picture, there were observations, a set of observations that were being made that began to point out that matter wasn't really behaving and reacting like a continuum. That matter was behaving more like it had some discrete nature to it. So what were those observations? Well, one of them was by this gentleman here, Robert Boyle. And guess what his formal occupation was? Chemistry? Yeah, that's a good guess, but his formal occupation was a theologian, as most scientists were at that time. And you, of course, know him for the empirical observation that the pressure times the volume is constant as long as the temperature is constant. But he actually advanced one of the first ideas of an element. and that is he called an element a certain primitive, unmingled body, and that somehow you can take these primitive, unmingled bodies and put them together to form a perfectly mixed body, a compound, a molecule. So this was one of the first ideas of an element that comes together to form elements that come together to form molecules. And then there was this gentleman, Joseph Priestley. Guess what his occupation was? He was a priest, of course. And what did he do? Well, he looked at reactions with dephlogisticated air. Dephlogisticated air reacting with materials. And what he observed was that these materials reacted more vigorously in dephlogisticated air. Well, what's dephlogisticated air? Well, of course, now we know dephlogisticated air is oxygen. It's air with the nitrogen predominantly removed. But it really took this gentleman, Lavoisier. It took this gentleman to really understand what Priestley was doing in his experiments. And what Lavoisier realized is that this dephlogistic air was kind of adding to the material when it did this reaction. And he made those observations, or he came to those conclusions by doing some very careful measurements of the mass before the reaction, so the mass of the dephlogistic air plus the mass of the material, and he found that indeed the mass after the reaction was equivalent to that before the reaction. And so he was one of the first individuals to realize that a chemical reaction can be written down analogous to writing an algebraic equation. Well, Lavoisier also did a lot of work with isolating elements. He identified 17 metals and 9 nonmetals as elements. Well, for all of his efforts, we all know what happened to Lavoisier. Because of his connection to the French monarchy, you know, the judge at his trial claimed that the Republic has no use for savants. Lagrange, at that time, a French mathematician, said it took but a moment to cut through that head, but it will require 100 years to produce another like it. Well, there was another Frenchman at that time, J.L. Proust. He was a little more politically savvy, so he hightailed it over to Spain and led a long and healthful life as a professor in Madrid. But what he did is he did some experiments, and he observed that when 2 or more elements combined, well, they combine to form a compound. They always combine in definite proportions by weight, and it didn't matter what the method of preparation was. And so because he made this observation over and over and over again with many different elements, this became known as the law here of definite proportions. Again, some indication that matter had a discrete nature to it. Right? It wasn't just a continuum. Some numbers were involved here. All right, but it really took this guy, John Dalton, English school teacher with a lot of interests. He was aware of the observations of Boyle and Priestley and Lavoisier and Proust. And what he realized is that he could begin to understand all of those observations if he went back all the way to Democritus and Democritus's idea of atomos, or atoms, these individual discrete particles of matter. And so he set forth some postulates which, of course, now are known as Dalton's atomic theory. But what he said is that each element is composed of atoms. He said that atoms of any given element are identical. He said that compounds form when atoms of more than one element combine. And he realized, of course, from Lavoisier's observations that atoms are neither created nor are they destroyed. Now, just an aside, John Dalton, with his breadth of interest, he also was the first individual to document color blindness in human beings. And in fact, we do call color blindness Daltonism. So see, we're getting you ready for medical school already. All right. Okay, but what I want you to recognize here is that Mr. Dalton didn't actually do any of the experiments himself. Although, from what I know of him, I think he could have done the experiments himself. But rather, he was aware of the seemingly disparate observations made by Lavoisier and Boyle and Proust. And he just said, well, you know, if I take those observations and I use this framework, well, then I can understand them. They make sense within this framework. And this is a powerful approach in science. A lot of science progresses this way. That is, that there's this collection of seemingly disparate observations, and then all of a sudden, somebody comes along and sees an organizing principle in all of those observations and puts forth then these postulates. That's what Dalton did here. Now, of course, these postulates weren't accepted immediately, and rightfully so, because they were just postulates. They needed further substantiation. And that further substantiation came in terms of the work by this gentleman, Joseph Gay-Lussac, the law of combining volumes. It came by the work of this gentleman. This gentleman is Lorenzo Romano Amedeo Carlo Avogadro's hypothesis. And of course, you can all read Italian, so you can read what's on this stamp here, right? It just says equal volumes of gas under the same conditions of temperature lead to the same number of molecules. See? You didn't know you could read Italian, but there it is. Okay. And further substantiation for this idea of an atom and the discreteness of matter came from this gentleman, Ludwig Boltzmann, gas kinetic theory, who proposed that, well, you know, pressure, that must be due to these atoms that are moving around and hitting the walls of a vessel. Those impacts give rise to the pressure that is exerted on the walls of that vessel. And then finally, it took this gentleman, Cannizzaro, and it took his statesmanship. Because what Cannizzaro did, and now this is the later 1800s or so, what Cannizzaro did is that he got the scientific establishment at that time. And the scientific establishment at that time, of course, is this small group of pale males. But he got them to listen to Dalton's atomic theory and then the ensuing experiments of Avogadro and Gay-Lussac, et cetera, et cetera. And finally, he got them to say, yes, there's something right about this atomic theory of matter, the idea that mass was made up of discrete particles called atomos, or atoms. Well, nowadays, we, of course, can actually image individual atoms or molecules. And what you see here is an array of 28 CO molecules. And these 28 CO molecules are arranged in the form of a little man or a little woman. I'll let you figure it out. But these are CO molecules sitting on a platinum surface. And so each one of these orange balls here is a CO molecule. But when CO binds to a platinum surface, it does so with the carbon end down and the oxygen end up. And there's a really good reason for why that is the case, and we'll talk about that when we talk about molecular orbitals. So what you're seeing here is really just the tops of the CO molecules. You're seeing the oxygen end of the CO molecule. All right, well, this image here was taken by something called a scanning tunneling microscope. And I'm sorry to say, but this was actually invented just before you were born. And it was actually worked on by Ruska and then perfected by Binnig and Rohr. And they earned a Nobel Prize for their work. And the way the technique works is the following. Let me maybe have the board lights here so that we can, I'm going to do some board work. Okay. All right, so what you do to do this is that you take a tungsten wire and you do a little chemistry. You etch the tungsten wire down to as fine a tip as you can. So you put it in some potassium hydroxide, you send some current through it, do a little electrochemistry, and what you'll get then is a pretty fine tip at the end of this tungsten wire. But then what you do is you take that tungsten wire and you attach it to a piezoelectric crystal. All right? So a piezoelectric crystal, and let me put it this way here. A piezoelectric material is some material that if you put a voltage across it, it expands a little bit. Little bit meaning 10, 20 angstroms. Okay? And so now, if you attach the tungsten wire to that material, you have some control on the angstrom scale. All right? So that's what happens in order to move that tip around. But then what you do is you take this tip and you bring it, say, within 5 angstroms of the top of this CO molecule. So if I have my platinum surface here and my carbon here, and here's my oxygen, all right? What I'm going to do is I'm going to bring this tip, say, within 5 angstroms here of this oxygen end of the CO molecule. Okay, and then I'm going to put a negative voltage on this tungsten tip here. And I'm going to take the CO molecule, I'm going to take the platinum surface, and I'm going to ground it. Now, in this tungsten tip, there are, of course, electrons. And since this is a metal has a characteristic where some of those electrons aren't strongly bound to the nucleus. They are actually, they actually roam around the solid. Okay? And this is a high energy state. Given that electrons are negatively charged and they're in an environment of this negative potential, hey, that's a rather high energy state for those electrons. So if I were to draw an energy level diagram here, so this is energy, and I'm going to represent those electrons on the tungsten tip, it's going to be at some high energy level. So this is electrons on the tungsten, all right? However, there are also some electrons down here, and they're at ground potential. So these electrons are at a lower energy. So I'm going to draw an energy level representing them. This is the electrons on the platinum, right? And so this coordinate here is kind of like a distance, right? This is the distance. This is the electrons on the tungsten. Over here, the electrons on the platinum. And what these electrons on the tungsten tip would like to do is to be here on the platinum, because that's a lower energy state. But the problem is that there's a gap right here. There's no material between the tip and the oxygen end of this CO molecule. If you do it in a vacuum, there's a vacuum here. There's a vacuum gap. And so for the electrons to go from here to here, well, there's a very large barrier. This is a very high energy state if an electron were in between this gap here. So I'm going to represent that energy change as the electrons go from the tungsten tip to the platinum surface as a barrier like this. All right, very large barrier. Now, you've seen these kinds of, we call them reaction coordinates in chemistry in high school. That is, you've seen situations where we might have, if we're doing an energy level diagram, this is the energy of the reactants. Out here, this is the energy of the products, right? And in between is this activation energy barrier that we call EACT. In other words, you have to put energy into the system in order to get the reaction to go. You have to put energy into the system before you get any energy back out, right? And that's what happens in a chemical reaction. We put energy into the system before we make it go or can make it go. But in this particular case, the electrons, they don't behave like most reactants. The electrons right here, you know what they do? These electrons, hey, they go right through that barrier. They don't care that there's a brick wall there, right? They just go right through the barrier. We call that tunneling. And how in the world can that happen? Well, that can happen because electrons, unlike most atoms and molecules over here, electrons are quantum mechanical particles. And they do not obey classical mechanical rules. And that's a subject that we're going to start talking about today and tomorrow and for the next few days. So these electrons, they just tunnel right through that barrier and get over here to the other side. All right? So that means in this experimental setup, if I were to connect a wire from this tungsten tip here to the platinum, and I put in an ammeter right there, so I measure the current, hey, I'd be seeing some current flow, some measure of this flow of electrons from the tip to the tungsten. And so that's what's done in the technique. All right, but now, how do you get this image that I showed you earlier, all right, from this kind of arrangement? Well, what you do is you now take this tungsten tip and you mount it on a piezoelectric crystal, which I forgot to tell you, sometimes piezoelectric crystal, quartz is a piezoelectric, barium titanate is a piezoelectric. But you mount it on a piezoelectric crystal that will allow you to move from side to side. All right, so I move now my tungsten tip over a little bit. All right, and I know exactly how much over I moved it because I've calibrated my piezoelectric crystal. But now, what do you see? Well, if you just moved it over, you didn't change the vertical distance, if you just moved it over, what do you think would happen to the current here? Decrease. Would absolutely decrease. Why? Because you've now, right, changed the distance between the oxygen and that tungsten tip. Over here on this diagram, you made this barrier thicker, right? And the thicker you make it, the more difficult it is for those electrons to get through, so the current's going to go down. So in order to bring the current back up, what you're going to do is you're going to take that tungsten tip and you're going to move it down slightly so that the distance now between the tip and the oxygen is going to be the same as it was in this particular position from here to here. So then you bring the current back up. But again, you know exactly how far down you move that tip and how far over you move that tip. Right? Okay, so you got now 2 points. Now we got to keep going. So what are we going to do to scan? Well, we're going to move this tungsten tip over again. And again, you know, the current in this particular case is going to go down. In order to bring it back up, you're going to move this tip further down so that the distance between here and here is the same as it was originally. So you reestablish the current. But again, you know exactly how far down and how far over you move the tip. And then what you do, you assign a different color to the different distances above the CO molecule. And if you assign different colors, you can get this image. So for example, if we can dim the lights on the blackboard again, and we'll look at the slide. Okay. All right, so if the tip is very far from the surface, we give it kind of a whitish color. And as it gets closer and closer to the surface, we give it a darker and darker orangey color. And then finally, when it's so far down that it's actually in contact or tunneling to the platinum, we give it a blue color. All right? So that's how you get this image. That's the basis of this technique. Okay. So now you also notice that these CO molecules have a peculiar arrangement. And this is not due to, in the most au courant language, intelligent design. Rather, this is due to a very patient experimentalist, i.e. graduate student, who spent 24 hours putting these CO molecules into this particular position. So how did he do that? Well, he did it in the following way. He first took a few CO molecules and put them anywhere on the surface, just exposed the surface to some gas. And then he imaged the surface to figure out where they were. And so if these CO molecules, or my balls, my soccer balls are the CO molecules, and if my foot here is the tungsten tip, right, he just imaged the surface, right, to figure out where they were, so he knew where they were. So then he's got to move these CO molecules. So he brings the tip, close to one of the CO molecules, and then if you put a voltage pulse on that piezoelectric and actually jerk the tip, well, you can jerk it such that you hit the CO molecule and it goes flying away. That's nice, but now where did it go? Well, in order to find out, you got to image the whole surface again, right? And you find that it is somewhere all the way over here, all right? Now you really want it over there, so you repeat the operation, and, well, 24 hours later, you get this little man. And I know it was 24 hours later. All right, so it's going to be a while before this kind of nanotechnology, assembling a molecule by molecule, beats the synthesis in a beaker to put the molecules where you want them. All right. But even though this kind of visual observation of atoms and molecules really wasn't possible 100 years ago, the evidence that I alluded to or quickly went through earlier was really quite compelling for the existence of atoms. And the observation or the belief that the atom was the most basic constituent of matter, the elementary particle. You couldn't have anything smaller than an atom. And in fact, at the end of the last century, it was generally believed that the theoretical structure of the universe was complete. Nature was understood. There were no more discoveries to be made. And after all, there were, by this time, in the late 1800s, a lot of advances. Well, Newtonian mechanics, that had already been known for 250 years, the mechanics that guides the motion of all bodies around us, even astronomical bodies. Thermodynamics was completely developed. Statistical mechanics was developed. Statistical mechanics, which relates the microscopic description of the behavior of matter to the macroscopic description of the behavior of matter. And also, there were these optics experiments of Young, Fresnel, and Hertz that seemed to put to rest the question of whether or not light was a particle or a wave. Boy, those experiments seem to be absolutely conclusive that light was a wave. those experiments demonstrated Maxwell's equations. Maxwell's equations that unified the field of optics and electromagnetism. So, by this time, there was all of these accomplishments. The idea was that everything was done, and the idea was remaining that the work that remained was largely to investigate the next decimal place. Everything else was done. However, at the same time, by the late 1800s, there began to be two sets of observations, two tracks of observations, that if you look closely, began to illustrate that maybe things weren't quite so clear. Maybe things weren't quite as well understood. And what were those observations? Well, one of those observations is the discovery that we're going to start looking at today, that the atom is not the most basic constituent of matter. That you can take an atom apart into an electron and a nucleus, at least an electron and a nucleus. So that's one track. The other track is that light appeared to behave in some cases like a particle and not a wave. And one of those cases is this observation here of the photoelectric effect. So what we're going to do is we're going to look at both tracks of observations here. And we're going to see how these observations made it such that it was impossible to explain how an atom held together, how an electron and a nucleus held together within the classical way of thinking, within the Newtonian mechanics, the mechanics that you're going to be looking at this semester in 801. You can't use that mechanics to understand how this electron and the nucleus stay together. You can't use that mechanics to understand how two atoms are bound together. We need a new way of thinking. And it's these two tracks of observations that led to the discovery, in a sense, of this new kind of mechanics that we're going to be talking about. Okay, so let's start on one of these tracks. And that track is a track of seeing that the atom is not the most basic constituent of matter. And the first observation is done by this gentleman, J.J. Thomas. It's the discovery of the electron. Okay, so I'm going to need the lights on again. All right. So what J.J. Thomas was interested in doing was understanding what discharges were made of. All right? So he had a glass tube that was evacuated, and in it he had what we're going to call here a cathode, and he had an anode. And as I said, a glass tube, he pumps out the air, and then he fills it up with hydrogen, H2. And what he does is he puts a large negative potential on this cathode. And on the anode, he puts a large positive potential, and he cranks up the potential difference here. And he keeps cranking it up until at some point the gas begins to glow. And it's at that point that this discharge here is ignited. And this is kind of a plasma. And he wanted to understand what's in this plasma. He's just curious. He wants to know. And so what he does is that he pokes a hole here in this anode. All right? There's a hole, and he lets out a little of this discharge. And he lets it out. And my chalk is breaking. And he lets it out. And way back here, he has some kind of a screen, a phosphor screen, so that not only does this discharge here kind of glow as it's moving along, but when it hits the phosphor screen, it lights up. Okay? And so that's nice. But then what he does is he takes two parallel plates and he puts it above and below this luminous beam. And there's a positive charge on one of these and a negative charge on the other. And lo and behold, when he increases this potential difference, this delta V, what happens is that this luminous beam, some of that luminous beam, is actually deflected a little bit. And so now there's another very bright spot, and he can measure this deflection, and we're going to call it delta X. Now, since some of this luminous beam was deflected toward the positively charged plate, what kind of particles did he decide were in this luminous beam? Negative particles, because they're attracted to the positively charged plate. So we called this deflection delta X. We'll call it delta X sub minus. Now, he knew enough electromagnetism at that time to realize that the amount of that deflection has to be directly proportional to how much charge was on the negatively charged particle, and I'm going to call that E sub minus, because the more charge, the easier it would be to deflect it. And he recognized that the amount of deflection has to be inversely proportional to the mass of that negatively charged particle. Because after all, the more massive that was, the more difficult it was going to be to deflect it. Right? And then what he did is he cranked up delta V as much as he could. And here I'm taking a little liberty with the story, but I'm telling you essentially the essence of the experiment, but it's a little more complicated than what it is I'm going to tell you right here. But he cranked that up. And when he did, he realized that there actually was some other particles that were being deflected toward the negatively charged plate. Just a little bit. All right? Not a lot. Just a little bit. And again, he could measure that deflection. And he called that, or we're going to call that delta X sub plus. All right? These got to be positively charged particles because they're attracted to the negatively charged plate. And again, he realized that delta X sub plus is proportional to the charge on that positively charged particle and inversely proportional to the mass of that positively charged particle. All right, but now, here comes his thinking. What he guessed is that these positively charged particles, he guessed that they were H plus, a hydrogen ion. How did he know that? Well, this is a guess. However, he did know that in this plasma, this discharge, that there were hydrogen atoms. And how he knew that is something we're going to talk about in a few days. But he knew that. He also knew H here, these hydrogen atoms that are produced in the plasma. Somehow the plasma breaks the H2 bond. These hydrogen atoms were neutral. Okay? And so he said, well, if it's a positively charged particle, well, gee, you know, it must be that something was removed from the hydrogen atom to make it positively charged, and that something must be this negatively charged particle that I'm observing. Okay? Because I know that originally, right, the hydrogen atom has to be neutral. So therefore, I'm going to guess that the magnitude of the charge on the negatively charged particle is equal to the magnitude of the charge on that positively charged particle. And if that's the case, then I can take a ratio here of the deflection of the negatively charged particle to the deflection on the positively charged particle. And since these two are equal, I'm guessing that, since these two are equal, well then this ratio has to just be equal to the mass of that positively charged hydrogen atom. to the mass of that negatively charged particle. All right? And now, here's the important point. The important point is that no matter how he made these measurements, no matter how he did that, the deflection for that negatively charged particle was much, much, much larger than the deflection for that positively charged particle. That then meant that the mass of this positively charged particle, which he guessed to be a hydrogen atom, right? That must be much, much larger than the mass of the negatively charged particle. But he also knew that at that time that a hydrogen atom was the least massive atom. But here's an experiment that showed that there was a particle that was less massive than a hydrogen atom. Hey, but up to then it was the atom is the most basic constituent of matter. You can't chop it up anymore. But here was the evidence that there was a particle less massive than the hydrogen atom. Eventually it's called an electron. But this is the first evidence here that the atom wasn't the most basic constituent of matter. Now, it actually took another 10 years with the milk and oil drop experiment to actually measure this ratio correctly and to determine the mass of the electron. We won't go into that. But this ratio here, you probably all know, the mass of the electron is about 836 times that of the mass of the hydrogen atom or hydrogen ion. Okay?